Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
Modern continuous integration pipelines are exceptionally efficient at producing code, but they are equally efficient at generating critical security vulnerabilities at a volume human engineers cannot possibly triage. Passive vulnerability scanners comb through these commits and flag errors, but they don't solve them. They simply pile up an ever-expanding backlog of alerts. Assigning a developer to investigate, verify, and resolve every single flagged line of code drains hundreds of engineering hours and carries an immense financial cost for enterprise security teams. OpenAI's Daybreak platform addresses this structural failure. It transitions an organization's digital defense from passive alert generation to active agentic remediation. The architecture runs on two core components: the reasoning engine of GPT-5.5 paired with the execution capabilities of Codex Security. To understand how this system operates, we have to look directly at its internal loop, specifically how Daybreak autonomously maps, patches, and logs vulnerabilities within live corporate codebases. As enterprise attack surfaces expand, human triage becomes a mathematical impossibility. Active, agentic intervention is the only remaining method to scale a corporate security posture. When Daybreak attaches to an enterprise repository, it acts as a continuous surveillance layer across the entire codebase. Traditional tools look for isolated syntax errors in a vacuum. Daybreak's initial detection phase scans the repository to understand the broader architectural context. Instead of just flagging a weak peripheral node, the model plots a specific vector through subsequent systems to reach the core. By tracking these paths, the system isolates active risk and prioritizes vulnerabilities based on a real-world exploitability. This analysis generates a continuous, editable security threat profile that is permanently tied to the live environment. Because the connection is live, the moment human developers commit new code, the system recalculates and updates the threat profile instantly. A static list of bugs offers no strategic value. Dynamic mapping contextualizes exactly how a breach will execute before it happens. Once the attack path is mapped, Daybreak switches from observation to active neutralization. The system assesses the targeted node and autonomously generates a bespoke software security patch designed to close the specific vulnerability. This segmented pipeline tracks execution. Daybreak moves the code into an isolated sandbox. Here, the AI acts as the adversary, deploying the mapped offensive vector against the patch block. The patch must block the threat, and downstream dependencies must remain intact without breaking surrounding code. If either of those checks fail, the loop resets. Daybreak discards the patch and instantly generates a new variation entirely without human input. A human DevSecOps engineer might spend hours manually writing and testing a single patch variation. Daybreak iterates through dozens of combinations in seconds. When a variation finally passes both checks, the verified patch is approved and deployed directly back into the live production environment. The system then takes the evidence from that sandbox execution, packages it into an audit-ready compliance log, and routes it to centralized corporate tracking platforms. This closed-loop sandbox architecture removes human engineers from the testing phase, eliminating the primary bottleneck in code verification. But running this automated loop exposes an inherent logic problem with using standard, off-the-shelf large language models for enterprise defense. To test a patch thoroughly, an AI needs to be capable of analyzing malicious code and generating highly effective adversarial exploits inside the sandbox environment. As seen in this logic tree, standard commercial AI alignments view this necessary adversarial behavior as a direct violation of safety parameters, resulting in an abruptly blocked request. This creates a halted loop. The model refuses interaction, and the automated remediation pipeline shuts down. Enterprise security teams frequently encounter this friction. When they attempt deep malware triage, standard AI tools simply refuse to process the requests. Commercial models are disqualified from executing deep cyber defense precisely because their public safety guardrails are functioning exactly as intended. OpenAI designed the Trusted Access for Cyber, or TAC framework, as a deliberate architectural bypass to this guardrail paradox. Organizations must pass strict vetting protocols and onboarding requirements to gain access to the program. This diagram outlines the framework's tiered structure. The wide bottom tier utilizes standard GPT-5.5 models, maintaining regular boundary parameters for general, everyday security workflows that don't require deep exploit generation. The middle tier is the trusted access level, engineered specifically with lowered refusal boundaries. This level grants verified DevSecOps teams the clearance to analyze live malware and triage complex vulnerabilities without triggering the friction of halted loops. Finally, the narrow top tier provides isolated access to a highly restricted variant called GPT-5.5-Cyber. This specialized variant is reserved exclusively for complex, multi-stage defensive operations and securing critical infrastructure systems. Effective artificial intelligence in cybersecurity requires this kind of bifurcated alignment, preserving strict safety protocols for general corporate use, while deliberately lowering those boundaries for vetted defense operations. Daybreak is an intelligent layer, not a replacement system. It is designed to embed itself directly into the infrastructure an organization is already running. At launch, OpenAI established integration partnerships with major industry giants, including Cloudflare, CrowdStrike, Cisco, Palo Alto Networks, Oracle, and Zscaler. Raw vulnerability data flows inward from those platforms into Daybreak. Once verified, the patch flows outward, feeding directly back into those deployment pipelines. By interlocking with existing tools, Daybreak scales its autonomous remediation across the entire attack surface of a modern enterprise network. For Chief Information Security Officers implementing the TAC framework, the daily operational focus shifts away from the manual verification of code. The objective of enterprise defense is no longer managing an endless backlog of vulnerabilities. The objective is now engineering and actively governing the parameters of an autonomous agent capable of neutralizing them. Enterprise security systems are largely built on a static foundation. Firewalls and signature-based detection layers are designed to hold a line against known threats. But when adversaries deploy dynamic, rapidly evolving attack vectors, they bypass those static defenses and overtake a network almost instantly. The initial industry response to this asymmetry was integrating large language models into the security stack. Yet standard commercial LLMs hit an immediate ceiling. As conversational assistants constrained by generalized architecture, they can summarize an attack report or suggest a defensive tactic, but they lack the capacity to take autonomous action to stop it. OpenAI developed Daybreak as an agentic platform that integrates directly into the enterprise digital defense stack to mitigate threats autonomously. The engineering engine driving this platform combines the reasoning capabilities of GPT-5.5 with the specialized programming logic of Codex Security. To establish immediate enterprise integration, the system launched directly into the corporate ecosystems of major cybersecurity providers, partnering with Cloudflare, CrowdStrike, Cisco, Palo Alto Networks, Oracle, and Zscaler. Daybreak alters the baseline of enterprise security by empowering the AI to execute autonomous remediation across the network architecture. Giving an AI the power to actively defend a network, however, introduces an immediate engineering paradox. Standard AI models undergo rigorous safety training designed to recognize and explicitly refuse to interact with malicious code. If you feed a malware sample into a consumer-facing model, it will trigger an automated rejection block to prevent the user from generating harm. A defensive system cannot ignore the threat. To conduct deep malware analysis or triage a live vulnerability, the AI must deliberately ingest, dissect, and process the malicious input. This creates what is known as guardrail friction. The specific safety protocols designed to keep the model secure render it practically useless for a specialized cybersecurity team trying to deconstruct a live attack. OpenAI's structural solution to this friction is the Trusted Access for Cyber, or TAC framework. It acts as a highly controlled gate, allowing specific deployments to bypass those consumer safety filters. Building an effective autonomous defense layer means systematically disabling standard safety constraints. Doing that without compromising the integrity of the model itself requires a strictly controlled, verifiable environment. This diagram illustrates how the platform maps a standard enterprise codebase architecture. The structure is intricate, consisting of thousands of interconnected nodes representing active repositories and live services. The platform's vulnerability detection engine crawls the repository to map the logical paths an adversary would use to traverse the network. Standard vulnerability scanning relies on static lists of known exposures. Daybreak improves upon this by charting context-aware logic chains. It isolates specific sequences of code that, while seemingly benign on their own, create an exploitable vulnerability when linked together. Once a path is identified, the system moves to its second operational area, threat modeling. Daybreak builds a dynamic security threat profile directly alongside the flagged nodes. Daybreak maintains continuous, editable threat profiles that update in real time as engineers push new commits to the live codebase. Transitioning from compiling historical vulnerability lists to mapping dynamic attack paths allows an organization to adopt a proactive security posture, anticipating vectors before they are ever exploited. Identifying a threat is standard practice. Daybreak's core differentiator is its automated remediation engine. When a vulnerable section of code is flagged, it is extracted from the live repository and placed into an isolated, secure sandbox. Within this contained environment, the AI engine generates a highly targeted software patch. It applies new logic directly to the isolated node, closing the specific exploit path. The patched code immediately enters a rigorous simulated testing phase. Daybreak fires synthetic attacks against the newly rewritten code to ensure the vulnerability is resolved without breaking the broader application logic. Only after passing this strict verification check is the finalized code routed out of the sandbox and deployed safely back into the live network. This closed-loop pipeline allows security teams to systematically burn down extensive vulnerability backlogs, executing hundreds of targeted microfixes around the clock without requiring human intervention for every pull request. When you authorize a large language model to autonomously write and deploy enterprise code, isolated sandbox testing becomes a mandatory architectural requirement to prevent the AI from introducing catastrophic system errors. This brings us to the final operational pillar, visualized here by the data pipeline, compliance logs. Every autonomous action taken by the AI, every threat detected, patch generated, and test executed is meticulously recorded. The platform compiles comprehensive audit-ready validation logs detailing exactly how and why a piece of code was altered. These logs are exported continuously, integrating directly with a corporation's existing centralized compliance systems to maintain a flawless operational paper trail. Executing this complete automated loop brings us right back to the engineering paradox. Finding the exploits and testing the patches requires the system to ingest highly malicious data. Autonomous remediation demands absolute transparency. Enterprise organizations cannot deploy opaque black box code changes to their infrastructure. They require the rigorous compliance tracking Daybreak provides to prove the network remains secure. Deploying this architecture into a live environment requires bypassing standard safety filters, which is why OpenAI manages distribution through the Trusted Access for Cyber framework. Daybreak's advanced features are not available as a simple plug-and-play API. It operates entirely as a highly restricted, gated pilot program. This flowchart outlines Step 1, the formal pilot request. When an enterprise applies for access, they immediately enter the organizational vetting protocol. OpenAI mandates rigorous scrutiny for all applicants. This process is a comprehensive, manual audit of the applying entity. The vetting protocol verifies the maturity and stability of the organization's existing internal security infrastructure, ensuring they possess the technical capacity to host agentic models securely. The audit also examines the individuals who will operate the platform, verifying the professional legitimacy and operational history of the security team members themselves. Balancing aggressive, autonomous capabilities against system safety requires absolute certainty in the humans operating the tools. That is why this structural vetting is a mandatory prerequisite. This matrix visualizes Step 2. Once an organization clears the vetting protocol, they proceed to tier assignment, which dictates exactly how much autonomy the AI is granted. The integration begins at the base tier. This level utilizes standard GPT-5.5 models to assist with high-level, everyday security workflows. At this tier, all standard consumer safety guardrails remain fully intact. Security professionals can then escalate to the Trusted Access tier. Here, the strict refusal boundaries programmed into the base model are deliberately lowered, directly eliminating the guardrail friction we discussed earlier. By dropping those blocks, the system unlocks the capacity for the vetted team to conduct deep malware analysis and perform granular vulnerability triage without the AI refusing the inputs. At the apex level sits the GPT-5.5 Cyber tier. This is a highly specialized variant of the model. Access is strictly restricted, reserved exclusively for executing complex, multi-stage defensive operations and securing critical infrastructure. With the appropriate tier assigned, the process reaches step 3, final integration. The vetted security team deploys the Daybreak platform directly into their established corporate ecosystem, activating the autonomous loop. By pairing active agentic remediation loops with rigorous vetted access protocols, Daybreak automates the heavy lifting of the enterprise defense pipeline. It provides a viable blueprint for deploying powerful cyber capabilities while structurally containing the inherent risks of unconstrained AI.